Hello, everyone. So today we have the honor of Beidi Chen giving us a talk on using LSH to speed up various algorithms like SGD. And Beidi is a student of Anshu Srivastava in Rice University and works on hashing and other related areas. So yeah, let's give it away to Beidi.
Okay, thanks, Craig. So it's my honor to speak here, and thanks for coming to my talk. And because our group really want to promote this new line of work. So around this whole talk, we're gonna talk about how we use locality sensitive hashing, no longer doing the nearest neighbor search, but as a sampling process to speed up some algorithms. So the agenda will be, I will motivating using two examples. One is how we do adaptive SGD using LSH, and another we want to do unique entity estimation with SGD. Then I'll talk about some hashing basics, just in case some of you might be new to locality sensitive hashing. And then we solve the SGD problem and unique entity estimation problem using our unique weapon. And finally, I'll talk about some ongoing work with the deep learning stuff, also using LSH. Let's start with the stochastic gradient descent example. Basically, you have a training data, you have a loss function, and you want to optimize you want to fit your model with the training data, so you have to update your parameters data in each iteration. And for gradient descent, you basically choose every single data point and compute a gradient of it, and then do the update. That's big O N. For SGD, it's faster because you just pick a random sample, so it's like a uniform sampling. You pick a random sample, you compute the gradient, and you do the update. So how do we compare these two algorithms? Gradient descent, of course, iteration-wise converge faster, because in each iteration, it considers the gradients of whole training data. But for SGD, it's slower iteration-wise, but because every iteration you just have the gradient for one single point, you optimize for that point. But it's much faster because it's just big O1. So overall, in large-scale optimization, we still prefer SGD or mini-batch because we can afford the computational time of gradient descent. Are there any better SGD? There's a whole line of work people try to reduce the variance for SGD. Because for SGD, the reason why it converges slower in iteration-wise is you choose a single point and you regard every single point the same weight. You sample them, use the same probability. And the simple theory tells us, it's very simple, you can just prove it by yourself, that if the probability that you draw the sample at that iteration is proportional to the gradient norm, that will give you the optimal variance. The intuition behind it is, suppose you can compute all the gradients for all the data points at that iteration. One of the points has very large gradient norm. What you do for gradient descent is basically average over all the gradients. And that large gradient will dominate. So by choosing that gradient to do the update at this time will be an optimal choice with higher probability. But there's a chicken and egg loop here, if you can observe that. Because by knowing that that's the largest gradient or that's a large gradient, you have to compute it. And you have to compute the whole gradients for everybody. And that's already big O. Why don't you just do gradient descent? If there's a way that we can break this chicken and egg loop, which means that the computational time to select an optimal choice of the point to do the gradient update is big O 1, where still there's a hope to beat SGD in time. So the existing lines of work, of course, they can optimize the variance, but in each iteration, they require more computation. So iteration-wise is again converge faster, but time-wise is not. That's the chicken and egg loop for this problem. Let's see a second motivation example. We have 350,000 records from the ongoing Syria conflict, the death record. It's collected from different resources, and they will contain duplicates or near duplicates. And what is the naive method to compute how many unique entities in these records? You basically do the pairwise comparison. That's big O n squared algorithm. And that will be billions of pairs you want to compare. So that's not feasible.
So how do you compare a pair?
So you just grab A and B, and the records will contain the information like first name, last name, maybe in Arabic, first name, last name, gender, location, date, this kind of information. You do a lexical matching.
Okay.
So no matter what operation you're doing, you have to do that big O n squared times.
Sure, but I'm kind of interested about the operation. So how do you match like Nick and Nicholas and stuff like that?
So there's an expert who know, it's an English example, but it's in Arabic.
Sure.
And yeah, so people do lexical matching, and their short names, long names, they probably look very different, but they're the same meaning in Arabic. And you can see the date of death, and you can see the gender, ages, this information.
So basically, to you, this data comes in some like feature vectors or something like this.
Yeah.
How do you work with it? So what is it like?
The death record is already have a lot of features, can be categorized or string features. So you just compare the similarity or some kind of similarity of the records. You may be thresholding it after you do the pairwise comparison. That's a naive way of doing it. And you can do that manually. If an expert can do a billion comparisons, that's not feasible. Okay, what is kind of feasible or the current state of art is to do some random sampling, like SGD doing. You don't compute the gradients for everybody. You choose one, and it's still an unbiased estimator. So what we do is we map all the records to a graph. And each vertex of the graph represents one record. If there's an edge between two vertex, meaning that these two records belong to the same person, they're the same person. And the task is reduced to compute the connected components, how many connected components in the graph. So how we do that using the random sampling based idea is you can either sample a bunch of edges, pairs, or you can sample a set of vertex and compute if they have edges between them. And that's reducing the time for computing the pairwise comparison. But you're likely not getting any information because the graph is tend to be sparse. And what you sampled is tend to be all singletons. So because it's rare to have an edge, and you do a random sampling. So if your sample data doesn't have any edges, you can do upsample to estimate how many clicks or connected components in the graph. So that's the problem for random sampling. If there's a way we can know all the similarities, pairwise similarities of all the records, and we sampled based on that similarity to form our subsampled graph and do upsampling. That would be great because there's much information in the graph. These two SGD problem and unique entity estimation problem seems totally irrelevant, but they have something in common. They both need an algorithm which can estimate some sample based on some probability that you don't want to you don't want to do the computation. And we'll use our unique weapon, locality sensitive hashing, to solve these two problems. It's the similar ideas. And I will start introducing the hashing now. So all of you should heard of the usual textbook hashing. You just have a mapping from x to y, and if x1 is not equal to x2, ideally, you don't have collisions for y1 and y2 as well. So that's like hash map stuff. And then we have the randomized or probabilistic hashing. What does it do is, instead of randomly mapping items to another item, we do a probabilistic thing. If two vector or item are similar to each other, you will have a higher chance to share the same hash code. And if you are not similar to each other, the colliding probability will be low. Here's an example of one hashing technique. It's called sign random projection. It's like SimHash. And what does it do is, let's say for vector, these two vectors, the green one and the yellow one, you want to see what's the cosine, you want to estimate the cosine similarity of these two data points. So there's an angle there. What you do is you draw a random hyperplane. And then you do the inner product of this random vector with both of the vector. And you will get a result. If that is larger than 0, your hash code is 1. If it's less than 0, your hash code is 0. So in this way, what's the intuition behind it? It's a random hyperplane. If the two vectors are very close to each other, they're likely to have the same hash code. And what is locality sensitive hashing usually doing is usually for near neighbor search. Because it's similar to Google image search, they have a whole bunch of images in the database. When you use a query image, you want to search for the similar images, you can't do the big O and linear scan of everything in the database. You have to have something to index it. And using locality sensitive hashing is the best way to do that, because you store the image based on some similarity. So similar images will have the same or similar hash code. When you have a query image, you also generate the hash code. And it's a big O1 computational time, lookup time to retrieve the similar images. So that's super fast. So what LSH doing is usually for image information retrieval nearest neighbor search. I just talked about how you generate one hash code, and one random hyperplane won't work. You have to have a lot of them. So what you're basically doing is you have to have k hash function for each hash table, and you have to have L hash tables. And what you're doing for each hash table, k hash code needs to match to lie in the same bucket for two vectors. So the probability of this, if two vectors colliding for one time is p, then it's p to the power of k. And you do that for many tables. So it's 1 minus p to the k, and to the l, 1 minus. So that's the probability, and you can tune this k and l for different properties you want. But is LSH really only a search algorithm? We think it's not. Because what basically LSH is doing is, given a query data, you have some probability. When you query something out, that probability you can estimate. And you are basically doing an adaptive sampling process. You are sampling the points that is close to your query. Of course, all the probabilities doesn't sum to 1, and the samples are correlated. But that's fine. We can make it work. whenever you want to estimate a function f of x, you want to estimate the summation of f of x for all the x1, x2 till xn. You sample some of them and then divide it by the probability of sample them. That's still an unbiased estimation of the sum of f of x. And what LSH can do is it queries out some of the points, which is a subset of f of x. And we can compute the probability of retrieving them. And if we divide it by that probability, it is still an unbiased estimator. And if you're kind of confused on this part, let's go to the real examples. Let's recall what we introduced initially with the SGD problem. Remember, our task is to sample a data point we want to update on this iteration based on its gradient norm. But we don't want to compute the gradient norm because that's too costly. And how the LSH can help here is, for example, linear regression, square loss, is theta x minus y squared. The gradient of it is 2x times theta x minus y. You can decompose them into two vector inner products, xx norm, y norm as a vector, and theta minus y as another vector. If your input data dimension is d, your label is 1, then these two vectors are both d plus 1 dimension vectors. And your gradient is the inner product of it. And the norm is the norm of it. If we can put all the x, xi, y, xi, this input data points into the hash table, it's a one-time cost because you just put them in those hash tables initially. And in each iteration update, theta t, you have different theta each time. You hash this theta t minus 1, this vector. You have a hash code. You can retrieve the points from the hash table, the xy's. And you want to retrieve them to do the update and divide it by the probability of retrieving them. Why is the lower variance? Because you are likely to retrieve the vector that is similar to your theta minus 1, which gives you a larger inner product. Remember what we want to do? We want to sample based on the probability of, we want to sample based on the probability proportional to the gradient norm. And now we're sampled based on the probability monotonic to the gradient norm, which is a much better algorithm than regarding each sample equally, like SGD is doing. And there's only a little bit extra cost. It's only 1.5 times of the SGD is doing. Check all the literatures of variance reduction SGD. The computational cost is much more than that, because they have to record or compute some information on the past gradients. Otherwise, there's no way to do this reduction. But in this case, we make this smart way of saving the xy's in the hash table and query based on the probability that's monotonic to the gradient norm. We can retrieve not the optimal, but better points we want to do the update in this iteration. And of course, we can compute that it's still an unbiased estimator. And the variance is actually based on the distribution of the input data. If it's like everything is random, of course, SGD will work because they'll equally be the same. But if the data is well structured, which means they're clustered nicely, which is usually our regression or classification task data looks like, then LSH is always can retrieve that set of points that will do the good thing for that iteration. And this is some experiments results for linear regression data sets. It's called year prediction, and that's costlier. It's USAI dataset. And you can see on the top, it was for the plain SGD and our algorithm. And on the bottom is for SGD plus the AdaGrad and our algorithm with the AdaGrad. So I want to emphasize here, so our algorithm is also kind of independent of those learning rate optimization algorithms. Because whatever you can do to SGD, you can still apply it to our algorithm. That's not a contradiction. So we can see the red line convergence. This is time-wise. SGD is super fast. It's only one random number generator and just the gradients update. And we're beating them in time.
What's slice training cost?
Sorry?
Slice.
Slice is a dataset name.
Oh, okay.
So wait, sorry, I was distracted by something else. So for which losses can you do this?
Sorry?
So for which losses can you do this?
This is the experiment for the square loss.
But in general, like...
In general, we can also do the logistic regression as well, because that's e to the power of theta times x.
Okay.
Still some inner product. But this is some preliminary results for the linear regression.
Can you do SVM this way, like hinge loss or whatever it's called?
We haven't experimented on that. We're still like extending this to as much as possible.
Right.
But this is some preliminary results that is really nice. So the idea is here.
Is there, do you have other methods for like variance reduction that you compared against?
None of the methods do the extra computation in bigger one. The time-wise, you won't beat.
Fine, but also you're saying like if you put it on the chart, you won't.
You won't even.
It's like
Yeah, for time-wise, nobody compared to the plain SGD time because it's too fast.
So
Yeah.
these are all convex problems, I
Yes,
think.
yes, exactly.
Okay.
Those are the convex problems. For the non-convex, we're not that sure, and we're trying to exploring that as well.
Okay.
That would be super interesting because for example, deep learning, those neural networks
Yeah.
problem, that would be super interesting. Yes.
Because there's a lot of work on saying that SGD can kind of escape, for example, the local minima.
Yeah, exactly. So whatever SGD works, it works. SGD doesn't work, you won't make it work. Yeah.
How does this method change the covariance of the gradient, of the stochastic gradient?
So this is the covariance of it. And when you try to analyze it, there's no closed form to saying that this is beating the SGD invariance. But if you analyze the structure of the data, I just mentioned, if the data is like Gaussian, there's no way you can beat it because it's nicely distributed. But if it's clustered, think about it, LSH can kind of keep them in the different buckets. When you do it, similar ones will be retrieved, and that's usually the best for that iteration.
Do you know how the covariance matrix looks like?
What do you mean?
So
This is the
sample this
covariance.
way, like what is the covariance matrix of your sampled gradient? How does it look like? Because now you're weighing in the covariance matrix, the sum of outer products, you're weighing the outer products differently. So so the reason I'm interested is because I think why SGD works very well also depends very much on the covariance structure of the gradients.
Right.
If you have isotropic noise, it doesn't work as well. So the question is, how does this change the covariance structure of the gradient?
We can look into that. I haven't looked into it.
Cool.
So this algorithm that you presented, this is assuming that you're doing SGD just based off of a single points gradient.
If it's batch grade, if it's mini batch, it's also work the same because you don't retrieve one single point from the hash table. You can retrieve as much
But that
as you want.
doesn't, just from a practical perspective, that doesn't increase the lookup time.
That's even make it better because mini batch, you just retrieve them once, right? So it doesn't increase any computational time. Yeah, it works for batch gradient. Mini batch. Yeah. Okay, and this is some sanity check of we really retrieve the gradients that's better than SGD. So the red line, that's the gradient norm for the first two plots. And the red line is our algorithm. Every update, the gradient we do, the point we choose, the gradient norm is like much higher than what SGD usually choose. Okay, let's step back from SGD for a while. Recall the second problem we talked about. We want to estimate the number of connected components of a graph using some adaptive sampling. And we don't want to compute the pairwise similarities of each of the vertex because that's big O n squared. And it's very similar to the SGD problem. And we can also use LSH to tackle this problem. How we do that is, remember we have maybe hundreds of hash functions for locality sensitive hashing for all kinds of similarities. For SGD, that's for we care about the angle of two vectors. So we use sign random projection. For this one, what's the similarities of two records? Is string. So we use one hash function called min hash. Min hash is for the Jacob similarity of two sets. It's the collision probability. So if you just parse a string into 3 grams, and the min hash collision probability corresponds to set A intersect B divided by.
How does it take into account that like short name can be the same as long name that completely doesn't capture it? So you also need
you can capture it, but there's
but
a
you said
probability.
that you have some experts for
Yeah.
this thing, so that okay.
Yeah, anything that's pairwise comparison cannot catch, we can't catch it, but we won't miss it because LSH is a probabilistic thing. It says
Well, you would imagine that you have some way to like bring the name to some canonical form and then use your method. So if that would be possible, so you don't need to spend like n square time on.
Yeah, there are some algorithms that you can do the blocking. For example, you can fix one dimension of the data, one feature of the data, and then do like split them into. What I was saying is LSH is not deterministic. Even two vectors or even two records are not that similar. There's still a little bit chance of colliding. So you probably won't miss it. Okay, what we do, the whole flow is you parse the records into 3 grams or n grams. And then you apply a hash algorithm called min hash on it. Then you generate, remember what we do is when you have a set of data, you pass them in the hash table. Each bucket in the hash table, you can regard them as candidate pairs. If A, B, C, they're in the same bucket, meaning A and B and C, we probably think they're the same entity. In this way, we have a list of candidate pairs. Of course, there will be false positives. Maybe they're not a pair. I still hash them in the same bucket. In this way, we should do some filtering, like human labeling, or maybe training a small known samples and do the SVM or decision tree on it. Doesn't matter. We filter the false positive. Now, we have a list of the real candidate pairs, which will form a subgraph of the hidden graph. The hidden graph, we don't know. You want to estimate the connected components. But now, using LSH, you have a subgraph of it. And you exactly can estimate the probability P here if the edge in the original graph is breaking or not in the hidden graph. So intuition here is, in the original graph, it's a singleton. It has to be a singleton, 100% to be a singleton in the observed graph. If it's a pair, there's a probability that the LSH has the probability of sampling the pair based on the similarity. So the pair will have probability P to maintain and 1 minus P to break. And if it's triplets, it can break in 4 ways. And you can compute all these kind of probabilities and reverse them by counting how many singletons, pairs, or triplets in the observed graph to estimate how many connected components in the original graph. And it's, again, LSH is producing a yes?
Sorry, it's Pretty much in the original LSH paper, there was an algorithm for approximate connected components based on LSH. So what is the connection between them, or is it just the same thing?
There's the original?
In the Indigo Money paper, there is a algorithm for connected components based on LSH, approximate connected components.
Oh, I didn't know that.
Oh, so it might be, it's probably related. I don't know exactly details.
Oh, okay. If you can send me the paper, then that would be great.
Just open the
Okay, yeah, sure. I'm not aware of that. Okay. Yeah, you will produce unbiased estimator, and the variance will be very low compared to the random sampling method. And there are some results of the data sets, and those are random sampling based method, the green lines and the blue lines. And the red lines and black lines is the LSH-based sampling method. It's like magnitudes better for estimating the unique entities in the near duplicate data sets. And so the ongoing work is, first of all, we obviously want to extend extend the idea of the adaptive SGD to different kinds of problems like neural network. But that is not as easy as linear regression, because you can't decompose the gradients to a two inner product or something. But as long as we can get something better than random, and our cost is negligible, then that's a success. So there's hope there. Maybe not a clean form, but there's hope there. And we also want to do the adaptive sampling for choosing high activation nodes in the neural network, because, for example, ReLU, you compute the activation. There basically, most of it will be zero out. You would rather not compute in it. If you know that that will be low activation, you would rather not compute in it. But again, if you want to know that's a high activation or low activation, you have to compute them. It's another chicken and egg loop, but you can break it again using LSH, because that's basically inner matrix multiplication.
Wait, so Anshumali has paper on this already, right?
Yeah.
So
we are now extending this one to the large scale. That's like a proof of concept paper. Mm-hmm. And we want to do that in Amazon scale data sets.
So what's roughly the status? What can you do using?
Because we want to beat the time of TensorFlow.
Okay.
Yeah.
But I guess the problem is this is not GPU friendly, this approach. So
yeah, we want to beat TensorFlow in GPU using CPU, by using smarter algorithms.
Okay.
Yeah, that's very hard to implement. We're developing this now, and I'm still debugging every day. Because we have to write the whole network from scratch in C++, only use primitives and avoid all kinds of costs, because we're not doing those smart optimization in the engineering part, but we want to use our smarter algorithm to beat TensorFlow. Yeah, but my advisor will give the talk on this on August 27. You're welcome to come to the talk. Yeah. Any questions? Okay, then I think that will be it. Thank you.